morning. Today's topic is algorithm for Walsh function. In the last lecture, we have discussed about representation of a signal in Walsh series, and we have seen that any periodic signal can be represented in terms of Walsh coefficients, where this is the Walsh function and this is the Walsh coefficients. And we have also seen how to determine the Walsh coefficients. This is the representation or an expression for determining the Walsh coefficients. Right. And we have also seen the relation between Fourier and Walsh coefficients. This is what we have derived in the last lecture. In today's lecture, we will be discussing about algorithm for Walsh function. I hope that by the end of this lecture, you will be able to apply the basic algorithm for determining the Walsh function of a given fault signal. So I'll start with an introduction to Walsh functions, and then we will develop a basic algorithm, and after that we will apply for Walsh functions. As already been said in the last two lectures that Fourier series and Walsh series, they are both are methods for representing a periodic signal. Fourier series represents a periodic signal in terms of sum of sine and cosine functions of various frequencies and amplitudes, whereas the Walsh series, it expresses a periodic function as a sum of Walsh functions, which are piecewise constant and orthogonal functions. And both of these representations, they have found their applications in signal processing, communication and control systems. And coming to Walsh functions, these were exclusively developed in order to reduce the burden on computers by using just only add and shift operations in fixed point formats. So we can reduce the burden of multiplying, dividing, squaring, square root operations, which we generally see in terms of trigonometric things. So computational simplification is made possible by the fact that Walsh functions are basically either +1 or -1, which we have seen in the last lectures. And the basic principles of digital protection using Walsh function, it consists of expanding the faulted waveform of voltage and current by using Walsh series, right? Where it consists of, as already said, this is the expression. K value will be varying from 1 to infinity. And this particular term, it can be any voltage signal or current signal or forward, whatever may be the signal. Any signal, any faulted waveform, if you want to analyze, first of all, you will be representing it in terms of Walsh series. And these functions are then used either directly or indirectly through the Fourier-Walsh relation. Or you can directly employ the Fourier-Walsh series also to determine the phasor of fundamental component and also harmonics. Thereby, you can design which filters you want to employ. Now, first of all, let us try to develop the basic algorithm for Walsh functions. You know that this is the basic Fourier series representation of any signal, where these do represent the cosine terms, whereas these represent the sine terms, whereas these represent the cosine terms. And this is the DC component. Whereas these two terms, they represent the fundamental component of the phasor, whereas these two terms, they represent the second harmonic. And likewise, you will be having multiple terms for multiple harmonics. Now, these are the Fourier coefficients which you do have got, and how to measure the fundamental component using Fourier series. As already been said, when you have this particular As already been said, your Fourier series will be having terms like this, right? And all the odd terms, they will represent And all the odd terms, they will represent the sinusoidal terms, whereas all the even terms, they represent the cosine terms, whereas this one represents the DC component. So the first two terms, they represent the principal or fundamental components, whereas the next two, they represent the second harmonic. The next two represent the third harmonic. So if I take nth harmonic, it will be represented by f2n and f2n minus 1. These are the RMS values of the real part and also the imaginary component of the nth harmonic. So for determining the measured impedance or the fault impedance, we generally employ f1 and f2, which are the fundamental components of both voltage and current. So this employing the determining the phasor, impedance phasor. So we do require V and I, and for that we can employ either Fourier coefficients or Walsh coefficients. It is easy to do with Walsh coefficient values. That's already been said. This is the representation of Walsh representation of voltage signal in terms of Walsh coefficients and also Walsh functions. These Walsh coefficients are determined using this particular equation. Right. So what is the relation between Fourier and Walsh coefficients? That is also we have tried in the last lecture itself. So this is the representation of Walsh coefficients and Fourier coefficients. You know that this particular A matrix, this is valid for this particular A matrix. So that's fine. When you want to obtain Fourier coefficients in terms of Walsh coefficients, you can replace this one. Instead of doing the inverse, you can directly just transpose the matrix. So this is one big advantage with the A matrix, which we do have. So once you do have Walsh coefficients, you can determine Fourier coefficients, or once you do have Fourier coefficients, you can determine Walsh coefficients. Whichever method is comfortable for you, you can use it for determining the fundamental component phasor. Now, how to apply this one for determining Walsh functions? Your job now is to develop a framework how to determine the Walsh coefficients, a step-by-step procedure. So first of all, the discrete Walsh functions. Most of the times what happens is our signals may not be continuously fed. So we will be using some sample and hold circuits, and we will be using some sort of multiplexers. So all the continuous time signals, they will be sampled and they will be sent to you in the form of discrete formats. So it is possible to reduce the amount of real-time computation by employing a fast algorithm. This is generally used to calculate the Walsh coefficients. A rough estimate of Walsh coefficients will be available for you. So let us consider a voltage signal of this fashion. Right. So this is the periodicity. Now I am taking n samples out of this one. So total of n samples have been taken, and this is my total time. So the sampling interval delta t is equal to t by 10. Okay. So the sampling interval delta t is related to the time over which the signal is periodic and the number of samples therein. So if I write this one in another format, this is the expression. This is what I have written here. And this voltage, or if I take it as voltage, so the voltage at these instants of time, let it be, see, these instants, let them be t1, t2, t3. The initial one, let it be t0. So this is going to be tn. So tj is equal to j into delta t. Okay. So, and voltage at that particular instant, let it be v of j into delta t. So I am taking the previous assumption which we have taken in the last class, the delta dash t dash is equal to delta t by t. So this is my Walsh function, and the Walsh coefficients are now obtained using this particular revised expression which we have seen in the last lecture itself. Now how to determine this Walsh coefficients when I do have this discrete data instead of continuous time data? So for that one we can employ the trapezoidal rule. See, I may not be able to compute the integral because I may not be having this continuous time signal. So in that case, what I'll be doing is, rather than a time signal, let us suppose rather than that, if I do have these particular values. So as per the trapezoidal rule, you know how to apply the trapezoidal rule. Integration of this function or this entire time, it can be done by all the samples they are supposed to be taken. The first and last sample, they should be taken only half. First and the last. The remaining you can take it full. And then you divide it with number of samples which you do have votes. 1 by n. So this is the simple procedure how to determine the average of the signal. Sorry, integration of the signal. So the same trapezoidal rule I am applying here. So this integral of f of t from 0 to t, I am doing it in terms of discrete things. So these are the discrete values. See, the first term and the last term I am taking as half, whereas the remaining terms I am taking them as full. So this is the way how to determine the Walsh functions when you do have the discrete signals. Now, if I rewrite that one in a simplest format, now see, I'll take this one, this entire signal as f0, and I'll take this one as, see here, f1, and this is f k, and this is fn. This is fn minus 1. So in that case, I'll take, this is a simple expression where f0 is nothing but here at time t is equal to 0, f1 is equal to time t is equal to first instant. So in this way, Walsh coefficients are evaluated. As each new value of sample f of t is taken, then the old value will be dropped and the new sample will be added. Let us suppose if I want, so let us suppose I do have about 5 values. So if I want to perform with this one, I'll be using this particular formula. Now let us suppose if I want to perform with these signals, what I must do, I must consider only these parts. So in that case, what I'll be doing is, I don't want f0 signal, I'll be starting with f1 signal. So I'll be taking as half f1 plus f2 plus f1 now becomes, sorry, this was the original formula, sorry, right? This will become full, whereas the next one, n plus 1, it will become half. Okay, so this is the way how to determine the phasor. Right, so this is what I have, this is the representation. You can go through this, we will discuss it in the class. Right, so this is the representation. If you carefully see, when I do have a new signal which is present, fn plus 1, right, this is a generalized expression. For n is equal to 8, you will be getting this one as this. Any 8 samples you can take here. Now, when new samples do come into picture, see, old samples will be removed and new samples will be added. Right. Similarly, this is W0. Similarly, W1 also you can carry out. Similarly, W2, W3, W4, W5. For n is equal to 8, you will be having up to W8. So this is these are the expressions which give you better results to compute for Fourier expressions. Right. So I have mentioned here W2, W3, W4, W5, W6 and W7. Right. So try to remember these problems, these equations. We'll do problems in the class. So as already said, Walsh functions are helpful for us in analyzing a signal. So whenever the signals are basically fundamentally regular in nature, then it's better to use Fourier coefficients, Walsh coefficients, and represent the signal in terms of Walsh functions rather than Fourier coefficients. Okay. So I hope that now you are able to describe the basic algorithm for determining the Walsh coefficients, and I hope that you are now able to determine the Walsh functions and Walsh coefficients when you do have discrete data sets. Thank you, and prepare this question well, and I'll be asking someone of you, you are supposed to answer it in detail in the class. Thank you.